Hi everyone. Today we're going to explain Gay-Lussac's law, which is one of the most fundamental gas laws in chemistry. Gay-Lussac's law states that the pressure of the gas is directly proportional to its temperature, as long as the volume and amount of the gas stay constant. This means that when temperature increases, pressure also increases, and when temperature decreases, pressure also decreases. The equation for Gay-Lussac's law is P1 over T1 equals P2 over T2, where P equals pressure and T equals temperature in Kelvin. It is very important to remember that temperature must always be in Kelvin, not Celsius. This law helps explain real-life situations like why a heated aerosol might explode, or why car tire pressure increases on hot days.
When temperature increases, gas particles gain more kinetic energy. This means that they move faster and collide with the walls of the container more often and with greater force. These stronger and more frequent collisions increase pressure. A real-world example of this is a pressure cooker. When the temperature inside increases, the pressure builds up, allowing food to cook faster. Another example of this is car tires. On hot days, the air inside the tire heats up, increasing the pressure, which is why tires can sometimes burst if overinflated. So overall, Gay-Lussac's law helps us understand how temperature changes affect pressure in closed systems.
In this demonstration, we heat a small amount of water in a soda can, then place it upside down in cold water. The rapid cooling decreases the temperature and pressure inside of the can, causing it to collapse. This shows how decreasing temperature lowers pressure, which directly portrays Gay-Lussac's law.
Joy, look at me. Let's go. For our second demonstration, you need a heater, a balloon, a bucket of cold water, and a beaker with water. You place the beaker of water on top of the heater so it can heat up, and then when we place the balloon on top of the beaker with hot water, the balloon expands. This is because the air inside heats up, increasing pressure and pushing outwards. And then after that, you take the balloon out and you place it in the bucket of cold water. And when you do that, the balloon shrinks because the temperature and pressure decrease. This directly shows Gay-Lussac's law.
In this experiment, I placed a candle in a shallow container of water. I lit the candle and let it burn for a few seconds. Then I carefully covered the burning candle with an inverted mug, creating a fixed amount of air inside a constant volume system. After a few more seconds, the flame went out completely. Now watch closely as the water level rises into the mug. This happens because once the oxygen is consumed by combustion, the carbon dioxide produced has nowhere to go and fills up the space left behind. As the carbon dioxide builds up, it pushes against the remaining oxygen molecules, causing them to move closer together, with fewer gas particles taking up the same space. The pressure decreases significantly. The external atmospheric pressure remains constant, but the internal pressure drops dramatically. When the pressure difference between outside and inside becomes too great, atmospheric pressure forces water from the container into the mug. This demonstrates Gay-Lussac's law perfectly. For a fixed mass of gas at constant volume, pressure is directly proportional to temperature. While the candle was burning, the air heated slightly, increasing its pressure. But after the flame extinguished, the cooling air decreased its pressure, allowing atmospheric pressure to push water upwards.
Gay-Lussac's law is important because it helps us understand safety in real life. For example, it explains why gas containers explode when heated. It helps engineers design safe pressure systems, and it is used in engines and industrial processes. In conclusion, Gay-Lussac's law shows that temperature and pressure are directly related when volume is constant.